Hello, this is Dr. Hanaa Assil, and this is Unit 3, January 2024 in the Pearson Edexcel International A-Level Chemistry. So let's take a look at the questions. This is the first question. This question is about the hormone testosterone, the structure of which is shown, and we're asked to give the name of each of the three circled functional groups. So, functional group 1. Can we see where group 1 is? What is this functional group? This is a ketone. Where we have C double bond O, that's a ketone. What is the functional group 2? That's the one that has a double bond, so that is an alkene. What about functional group 3? The one that has an OH, that is an alcohol. Then the question says, describe a chemical test and the expected positive result for both functional group 2 and functional group 3. So what was functional group 2? That was the alkene. So what is test for alkenes or test for unsaturation? We said we add bromine water. It turns from orange to color. What about functional group 3? That was the alcohol. What is test for alcohols? Add phosphorus pentachloride. When you add that to an alcohol or to an acid, we get misty or steamy fumes of hydrogen chloride. So the result here is steamy fumes or misty fumes. In a mass spectrometer, the molecular ion formed can break apart into smaller fragments. One way the molecular ion can fragment is shown by the dashed line. So deduce the M over Z, the ratio of the fragment shown by the unshaded area, assuming it forms a singly charged ion. So we're going to take that part that has been broken off from the original molecule and decide what is the M over Z with one singly charged ion. So that means I need to get the number of carbons, number of hydrogens and oxygen. And if we look at it, the number of carbons and hydrogen and oxygen are C6H8O. That's the positively charged fragment. Now, M over Z, if Z is 1, that means I'm just getting the MR of this. The MR of this is the total, of course, of the mass numbers is 96. When molecular ions fragment, they form a smaller ion and another type of particle. State the other type of particle formed. Please note that when we fragment or break up these molecules in the mass spectrum, it forms smaller fragments, smaller ions, and it forms free radicals. A free radical is a species with an unpaired electron. Question 2 says, an experiment was carried out to determine the concentration of citric acid in lemon juice using titration. 3 students used the following procedure. Add 24 grams of lemon juice to a 250 centimeter cubed volumetric flask. Make up the volume of the lemon juice to 250 using deionized water. Mix thoroughly. Pipette 25 centimeter cubed of this diluted lemon juice into a conical flask. Add a few drops of phenolphthalein indicator. Titrate the diluted lemon juice with standardized sodium hydroxide of this concentration. Student A obtained the results shown. So these are the results of the rough titration plus 3 other repeat titrations. Draw a circle around the concordant results. Remember we said we repeat titrations until we get concordant results, and you should know concordant results are those that are within 0.2 of each other. So the difference between them should not be more than 0.2. So which of these have a difference of 0.2 or less. So of course the one that says 24.3 and 24.2, these are concordant results. The other ones are way off, so we don't include them when we calculate the mean. So when we calculate the mean titer, I use the ones that are concordant. We add them, divide by their number. So this is the mean titer for this titration. The equation for the reaction between citric acid and sodium hydroxide is shown. State the color change that occurs at the end point of the titration. Remember, what did we put in the flask? Which one did we put in the flask? We put 25 centimeter cubed of the lemon juice, which is the acid, and then I titrated with standardized sodium hydroxide in the burette. So when we put the acid into the flask and we add phenolphthalein, what is the color of phenolphthalein on acid? That is colorless. So once we add the sodium hydroxide from the burette drop by drop, we add it until the first drop that gives a permanent pink. So we're changing from colorless to pink. Calculate the percentage by mass of citric acid in the lemon juice using your mean titer from B. So what did we do? We were told that we have 24 grams of lemon juice. We put it in 250 centimeter cubed, and then we took 25 of that and titrated it with sodium hydroxide, and the volume of the sodium hydroxide, or the average titer that we calculated, came out to 24.25. So we have volume of the sodium hydroxide used, we have concentration, I can get number of moles of sodium hydroxide. Number of moles is concentration times volume, so that is 0.103, times the volume divided by 1,000, because the volume has to be in decimeter cubed. This gives us the number of moles. Then we're asked about what? We're asked about citric acid. So we look at the equation that we were given. What is the relationship between the number of moles of citric acid and number of moles of sodium hydroxide? Well, obviously the citric acid, which is the C6H8O7 there, this is a 1:3 ratio. So the number of moles of citric acid is the number of moles of sodium hydroxide divided by 3. But this is the number of moles of citric acid in the 25 centimeter cube that we titrated. We had all our lemon juice in 250. So if this is the number of moles in 25, the number of moles in 250 would be that times 10. Now we have the number of moles and we have the mass in 250. The mass would be the number of moles times mR. This is the mass of the citric acid. We are given the molecular mass of the citric acid there, 192. So the mass of the citric acid that is in the lemon juice is 1.6 grams. We are required to calculate what? The percentage by mass. That would be the mass of the citric acid over the total mass of lemon juice times 100, and we want the answer in 2 significant figures. So our final answer is 6.7%. So just a possible reason why the value obtained is valid even though lemon juice also contains other acids. We were calculating for citric acid, but we are told that the lemon juice also has ascorbic acid and malic acid, but that's okay. Our value is correct, or in the correct range. Why do you think that's the reason? What's the reason for that? The other acids are probably present in very small amounts compared to the citric acid, so they will have very little effect on the value of the titer. So the titer that we have is regarded as the one that reacted with the citric acid and we don't need to take the others into consideration. Two other students, B and C, also followed the procedure to find the concentration of citric acid in similar samples of lemon juice, but student B added too much deionized water in step 2. What was step 2? Step 1 was the one where we measured the mass, or we weighed a certain mass of the lemon juice and we put it into 250, and in step 2 we make up the volume in the volumetric flask to 250. Remember, we put a certain amount in the 250 centimeter cubed and we add water up to the mark in the volumetric flask. That's how we should make up the solution. The problem here is the students were told added too much water, so they passed the mark that is in that mark in the neck of the volumetric flask. They added too much water and it went up above the mark. Of course, that has ruined this solution. We don't know now what is its volume, so there is no way of trying to calculate the mass of the citric acid in that solution. So we need, actually, he's saying, state how the student should correct this mistake. Well, they should just start all over again. Throw this out, wash the volumetric flask, weigh a new mass of the lemon juice, make a new solution by adding the water to the correct mark so that we have an accurate volume. Student C used sodium hydroxide solution that was labeled 0.103 mole per decimeter cubed, but that had been made several months ago and stored since then. So someone made up this sodium hydroxide solution and left it for several months, and then this student C came and used it for the titration. Explain what effect this would have on the mean titer compared to student A. Well, the problem is, first of all, if we leave a solution stored for a long time, well, some of the water may evaporate, and that means the solution inside that bottle has become more concentrated, and therefore I will need less of it in the titration. So my titer volume would be lower. Question 3 says, seaweeds absorb iodide compounds from seawater. If seaweeds are dried and heated strongly, iodine can be obtained from the ash produced. So the procedure they're using is heat the dried seaweed strongly to burn off any organic material. Add the ash produced in step 1 to 25 centimeter cubed of deionized water. Boil for 5 minutes. Filter off the remaining solid, collecting the colorless filtrate containing iodide ions. Add 2 centimeter cubed of dilute sulfuric acid, followed by 10 centimeter cubed of what we call 20 volume hydrogen peroxide solution. Extract the iodine formed in step 4 using cyclohexane as the solvent. Allow the cyclohexane to evaporate to leave behind the iodine crystals. And the first question is, suggest why the iodine containing compounds do not burn off. We're saying they're trying to burn off what? Any organic material. So the iodine is probably not organic, and it is probably made up of ionic compounds, or it contains ionic bonds, and that means it will be something that has very high boiling point, will not burn off easily. 20 volume hydrogen peroxide solution means that 1 decimeter cubed of the solution produces 20 decimeter cubed of oxygen gas when it decomposes completely. Calculate the concentration of the 20 volume hydrogen peroxide solution in moles per decimeter cubed. So we're told that this produces 20 decimeter cubed of oxygen gas. So we have the volume of oxygen gas. We can use that to get the number of moles. Of course, number of moles of a gas is volume over 24. So this is 20, it's already decimeter cubed, over 24. This gives us the number of moles of oxygen formed. And that means from the equation, I can get the number of moles of hydrogen peroxide. The equation shows that if I have 2 moles of hydrogen peroxide, it gives 1 mole of oxygen. So how much will give this number of moles of oxygen? So you multiply by 2. That's the number of moles of hydrogen peroxide. I can use that to calculate the concentration, because the concentration is number of moles over volume. And we are told up there that we're dealing with 1 decimeter cubed of the solution. So that means the volume is 1 decimeter cubed, and that means this is the number of moles per decimeter cubed. In step 4, the iodide ions in the filtrate are oxidized to form iodine. The reaction takes place under acidic conditions, and the hydrogen peroxide is reduced to form a single product, which is water. We are required to write half equations for each of these changes. So let's look at the first one. We're told the iodide ions change into iodine, and this is oxidation, and that means the iodide ions lose electrons, and that means this is how we write the half equation. So I have iodide changing into iodine, and remember that iodine is diatomic. That means I have to write it I2, and that means I have to balance with 2I minus. And then we're told that this is oxidation, and we should know that iodide to iodine is loss of electrons, so I should have iodine plus electrons. If I have 2I minus, I need 2 electrons to balance the charges. Then we need to write the equation for reduction of hydrogen peroxide under acidic conditions. When we're told under acidic conditions, that means it's the hydrogen peroxide plus H plus. Now, we're told up there that this gives a single product, which is water. That means I'm starting with H2O2 plus H plus to give H2O, and you need to balance. So we'll need 2 water after the arrow. If I have 2 water after the arrow, I've balanced the oxygen because I need 2 oxygens before the arrow, so I have to put 2 in front of the water after the arrow. But that means that I have now 4 hydrogens. I already have 2 in the H2O, so I will put 2 in front of the H plus. And of course, this is the reduction, so this is plus 2 electrons to balance the 2 H pluses. Now we're supposed to write the overall equation. If I have 2 half equations like this, how do I write the overall equation? We said, first of all, the electrons should be the same. So here they're the same. If they're not the same, I will have to multiply by something to make them the same so that I can cancel them. The overall equation does not have electrons. Then I just put everything before the arrow and everything after the arrow. If anything is repeated, then I subtract them and write the rest of it. But there is nothing repeated here. So this is the overall equation. State the color of aqueous iodine solution. You should know, what is the color of iodine solution? It's a brown solution. Describe how to carry out step 5 using a separating funnel. Step 5 says extract the iodine formed using cyclohexane as the solvent. So I have a mixture and I want to dissolve the iodine in it into cyclohexane. So we use a separating funnel. And when we're told that the density of cyclohexane is less than 1, that means the cyclohexane is the upper layer and the water or aqueous is the lower layer. Okay, how do we use? The question is basically saying describe how to use a separating funnel. And you should know how to use a separating funnel. So we add the filtrate to cyclohexane in the separating funnel. The tap and the stopper have to be closed, and then the funnel is shaken slowly, actually, inverted several times, and from time to time I should open the stopper or the tap depending on which side is upright. So if the side up is the stopper, I remove the stopper a little bit to release any pressure. Then I close the stopper, invert, and open the tap also to release pressure that builds up due to formation of gases. And then once I have shaken like this several times, I leave it so that the layers are allowed to settle down. Then open the tap to remove the lower aqueous layer. And remember, while we are removing the lower layer, that stopper should be open. So the stopper is open to allow air in to balance the pressure inside the funnel, and the lower layer is allowed to flow out into a container, and then the cyclohexane layer is then collected in a separate container. Please remember that this is how we use a separating funnel. The hazard symbols for cyclohexane are shown. State what is meant by symbol 3. You should be familiar with the meanings of the hazard symbols. So you see which one is toxic, health hazard, flammable, irritant, oxidizing, corrosive, explosive, environmental hazard. Can you see all of these? You're required to know these. So we're asked about symbol 3. So which one is symbol 3? That's the one that indicates that the liquid is a health hazard. Give 2 safety precautions that should be taken to reduce the risk in step 5. Assume that we already have eye protection, gloves, and laboratory coat. So what else can we do? We are told from the hazard symbols that the liquid we're working with is flammable, irritant, and a health hazard. And it evaporates easily and so on. So I should do the experiment in a fume cupboard. This is to avoid inhaling any of the gas, so it's not a health hazard. Keep away from open flame, so I don't put it next to the Bunsen burner because it is flammable. Question 4. This question is about experiments involving ethanol. Ethanol and water mix in all proportions. The percentage of ethanol by volume in an ethanol water mixture can be found by comparing the density of the mixture to the densities of ethanol water mixtures of known composition at a constant temperature. So we do this experiment for different percentages, and then we can use it to determine the density of a certain percentage. Okay, calculate the density of an ethanol water mixture. Sample A, 5 centimeter cubed of which has a mass of 4.75 grams. How do we get density? You should know that density is mass over volume. So we have a mass of 4.75. The volume is, and it should be in centimeter cubed because the density usually comes out in grams per centimeter cubed. So the 4.75 over 5, that is the density in gram per centimeter cubed. Then we're given that table and we're told plot a graph of density against the percentage. So we plot the graph. It looks a curve like this. Please remember to distribute the numbers equally, and you don't need to start from 0 so that you can use as much of the graph paper as possible. Then we're told determine the percentage of ethanol by volume in sample A. We already calculated that sample A has a density of 0.95. Now, if I want to use this graph to get the percentage ethanol, then I look for a density that is 0.95, go to the curve, go down, and that comes out to be about 38 Ethanol can be prepared by heating ethanol with acidified sodium dichromate in the apparatus shown. Explain why the reaction mixture is heated as shown instead of heating under reflux. Remember, we said when we're trying to oxidize ethanol using acidified sodium dichromate, we can either oxidize it to form ethanol, the aldehyde, and that is if I distill it off immediately using this apparatus as it is being formed, or I could continue to heat it for a long time, and that is using this apparatus which we call heating under reflux, but this will heat it and continue to oxidize it until it is oxidized all the way to ethanoic acid. So why are we using the simple distillation apparatus? This is to collect the ethanol, the aldehyde, as it is formed, so that it is not further oxidized to ethanoic acid. If we use heating under reflux, then what we get in the end is ethanoic acid, not the aldehyde. Explain why the water is passed through the condenser in the direction shown. Remember that in any condenser, when we're doing simple distillation, the water goes in from down and goes out from the top. Now, why is that? This is to make sure that the condenser is filled with water, no air bubbles, and this is for more efficient cooling. A student determined a value for the enthalpy change of combustion of ethanol using the apparatus shown, and were given a series of data. Calculate the energy transferred to the water. So basically we're required to calculate Q, and you should know that Q is equal to mc delta T. What is M? M is the mass of the water, and we said the mass of the water is the same as the volume. So if we say I have 100 centimeter cubed of water, it is the same as saying 100 grams. So that's M. C, we're always given 4.18. Even if we're not given, you should know it is 4.18. Delta T is the difference in temperature. So it's the big minus the small. This gives an energy in joules. So this is the quantity of energy transferred to water in joules. Then we're told to calculate the amount of ethanol burnt in moles. So we're trying to get the number of moles of ethanol, and we know that number of moles is mass over molecular mass. So if we go back, we'll find that the information given to us was the mass of ethanol burnt is 0.65 grams and the MR of ethanol is 46. So 0.65 over 46, this gives the number of moles of ethanol. Then calculate the enthalpy change of combustion of ethanol. So we're trying to get delta H, and we know that delta H is Q over N. We already calculated that Q is this value in joules, so we need to divide it by 1,000 to put it in kilojoules, divide by the number of moles we just got. This gives the delta H in kilojoules per mole. Have we finished? Of course not. We know that delta H must have a sign. So we go back and see, did the temperature go up or it went down? Before heating was 20, after heating it was 57. That means the temperature increased. This is an exothermic reaction. Delta H is a negative value. Then the last part of the paper says, whilst evaluating the method used in C, the student found a diagram of an alternative apparatus as shown. Explain 2 reasons why this apparatus is likely to give a more accurate value for the enthalpy change of combustion of ethanol. So, what is different in this diagram than the other previous diagram? So this was the previous diagram that we used. We just used a copper container, a copper calorimeter, and we just put the spirit burner below it. This allows more loss of heat. If we use this previous apparatus, this allows a lot of loss of heat to the environment, while this new diagram, what does it show? It shows that I have a copper coil going through the water, so it's basically taking the heat and distributing it through the water, because the copper coil is a good conductor of heat. And we also have a lid somewhere on top. All of this allows less loss of heat to the environment, and it is allowing oxygen into the apparatus. If we're providing a lot of oxygen into the apparatus, this gives less chance of incomplete combustion. And that's the end of this paper. I hope this is useful to you, and thank you for listening. Good luck on your exam.